This is Neil Patwari. I'm going to do an example of system design where I design a point-to-point microwave link. This example comes from the Michael Rice Digital Communications book, and it's exercise 6.36 in the book. And the problem statement begins with, consider a point-to-point microwave link illustrated below. Both antenna gains are 20 dB and the transmit antenna power is 10 watts. The modulation is 51.84 megabit per second, 256 QAM with a carrier frequency of 4 gigahertz. Atmospheric losses are 2 dB and other incidental losses are 2 dB. A pigeon in the line of sight causes an additional 2 dB loss. The receiver has an equivalent noise temperature of 400 K and an implementation loss of 1 dB. How far away can the two towers be if the bit error probability is not to exceed 10 to the minus 8th? This problem has a lot of information. I tend to like to kind of mark up what information I have on this diagram. So I'll start with the antenna gains being 20 dB. And we have a transmit antenna power of 10 watts. Then we have a modulation of 51.84 megabit per second. So that is our bit rate, which is, and then we have 256 QAM. So 256 QAM. And we have a carrier frequency of 4 gigahertz. And atmospheric losses, 2 dB. Incidental losses are 2 dB, and a pigeon in the line of sight path causes an additional 2 dB. So total, we have these 3 losses that are, and then we have an equivalent noise temperature of 400 K, and another implementation loss of 1 dB. So this, I'm going to add 1 dB over here as another loss given to me at the end, implementation loss. So the question is, how far away can the two towers be if the bit error probability is not to exceed 10 to the minus 8th? So here I have a spec for 10 to the minus 8th probability bit error, and I have to get to this range. Okay, so this is what I'm trying to determine, this range. And what I can see is that we're going to start here at the probability of bit error, and we're going to work our way up following this path where we're going to go down this way through this graph to get to the path length. Okay? I should also mention that this path loss model, it says that there's a pigeon in the line of sight path. So that's one hint that you should use the free space path loss model, or the freeze model. So as I said, I started over here with the probability of error. We have the modulation and the probability of bit error, and so we can use the formula for the probability of bit error in QAM to figure out what our EB over N naught needs to be. Okay, and so our probability of bit error formula says that the probability of bit error in 64 QAM, which here needs to be equal to 10 to the minus 8th, okay, where M is the number of symbols, and this is again the probability of bit error for square QAM, with here M is equal to 256. So just to keep track of the things that I need to keep track of, the square root of M is 16, log base 2 of M is 8, because I think one of the biggest errors is getting confused by the square root and the log base 2 of M. I tend to write them down first. And then I just start to plug in these numbers. So the square root of M minus 1, and then square root of m times 8 on the bottom, and then the q function of 3 times 8, and then m minus 1, so 255. Don't, make a mistake and put the square root of m minus 1 in there. And this is all multiplied by EB over N naught. To simplify, I've got so what I need to do, and this is the kind of the thing you perhaps are not used to, is to invert this Q function. So I'm going to move this 15 over 32 to the other side and get 32 over 15. And then I'm going to take the inverse of the Q function, and that's going to give me, and then I'm going to square both sides. I'll continue over here. And then multiply by 255 divided by 24. And that will be my EB over N naught. I'm going to get a 319.0. Okay, here's the key. You have to find this Q inverse from MATLAB or from your calculator if you have the inverse Q function. Most calculators wouldn't. They might have an inverse ERF function. So I think it's called ERF INV for ERF inverse. So that error function inverse is then able to take this argument, but of course you're going to have to scale by the square root of 2 and add a 1/2 because the ERF function is not exactly the Q function. In MATLAB, I will share my code for the Q inverse function. So, look for my QINV.m file in the files section of Canvas. Alternatively, you can use a function. You can use the function that I included in the lecture notes. It's just a graph. And the graph shows the inverse Q function, and you can use that function. I have a table as well that lists argument versus Q inverse for many different values of what the argument would be. These are things that you can use if you don't have MATLAB handy, like if it's on an exam and you don't have MATLAB available, then you can do this. You can use those tables or the graph. Okay, so I have the EB over N naught. And so now I'm over here, and I want to get to the C over N naught ratio. What I need to get there is this relationship that EB over N naught is equal to C over N naught times 1 over the bit rate. Here the bit rate is given to us. It's 51.84 megabits per second. So using this relationship, I can find that C over N naught is equal to 319.0 times the bit rate 51.84 times 10 to the 6th bits per second. And I'm using the mega, I'm translating the mega into 10 to the 6th. In reality, what I really want is the received power, and that's going to be this result times the N naught. So let's go and find out what the N naught is. We have the equivalent temperature as 400 K, so when I want to find N naught, it's equal to K times the equivalent temperature. Of course, K is Boltzmann's constant, 1.38 times 10 to the minus 23rd units of joules per Kelvin, multiplied by 400 Kelvin is our equivalent temperature. So the units, of course, will result in joules for the answer. Okay, these are really big numbers and really small numbers, so we just have to be careful with those numerical values. When I then multiply these together, the 3, my units are going to be joules per second, which is watts. And my power then is 9.13 times 10 to the minus 11 watts. Converting this to dB, so I have C dBm, dBW. Let's start with dB of watts. That's referred to 1 watt. That's minus 100.4 dB watts. And let's give ourselves some more space. We have this power. So now we're over here in the diagram. We're right here. And we're trying to use all of these relationships to get us back to the path length using the freeze model. So let's put up the freeze model. Okay, this is one case where it doesn't matter what R0 I pick because I'm using the free space model. These R0 squared in the denominator cancels with the R0 squared in the numerator. Okay, we're also going to need to put in this loss 1 over L. And we're going to take all this information from the plot from the graph that we have on all of these parameters. We've got 10 watt transmitter. The GT and GR were 20 dB. 20 dB converts to 10 to the 20 dB divided by 10, or 10 to the 2, or 100. So times 100 times another 100 for the receive antenna gain. They're both the same. We've got the wavelength. So I'm going to go back up here and I want to say that my wavelength is equal to the speed of light divided by the frequency. Speed of light is 3 times 10 to the 8th meters per second. Frequency is 4 gigahertz, so 4 times 10 to the 9th. 1 over second. And I'm left with meters, which is good. I always try to check my units. So I've got essentially 3 over 40. And so I plug in 3 divided by 40 meters. And then I divide by 4 pi and square this. I've got this 1 over r squared. And my loss is, there are 2 dB losses and 1 dB loss. That's a total of 7 dB, which when I convert that, it's 10 to the 7 divided by 10, converting from dB to linear again. And 10 to the 0.7 is 5.01, or just 5. And this results in, but I'm going to bring r squared to this side. And I'm going to bring PR to the other side. So I'm going to have 10. And then the 1 divided by 5.01. And the 1 divided by the C, which is 9.13 times 10 to the minus 11 watts. That's our received power. And I'm going to solve for that and take the square root. And what I'm going to get is that R is about 8.83 times 10 to the 4th meters, or 88.3 kilometers. Okay, that is our maximum range to achieve the 10 to the minus 8th probability of bit error.